This is Bhuvan Unhelkar, and it's my pleasure to welcome you to this module, which is Advanced Class Design. So, in the previous module, we came across identifying classes, naming them, putting attributes and operations in them, and then starting with the process of linking them together through inheritance and association. In this particular module, we refine those classes to move them into detailed design. As I mentioned in the previous module, each class is representative of a program. But in order to take a class right down to the code level, but still staying in modeling, we want to add many more details to that class. Sufficient for it to be very, very close to a program without being an actual program. So even in this module, once we embellish our classes with all the details, we will try and generate code using one of our tools, Star UML or Visio or any other tool that you might be using, in order to see how our class designs relate to the code that we would have otherwise written without the benefit of modeling. And once we understand how the code and the diagrams, particularly the class diagrams that we are drawing, relate to each other, then we have tremendous confidence and we are able to generate a lot of value through class modeling. So now let us look at the details of the class in design or in solution space. So I have given you attributes with their types. A serial number has type integer. Each attribute has a type. Then we have got name of type char, character. We have got date of birth of type date. So these int and char and num and date could all be provided by the programming language. These are pretty stock standard types. So each attribute has a type. And then as you see in the serial number example, I have also initialized the type. Because each of these attributes that we are defining in a class, when they are instantiated as objects, they will occupy a certain space in the memory of our computer. If we don't initialize attributes, then whatever is available in the memory will be addressed, and that could be garbage. So it is a good habit, good program design habit, to initialize the attributes. Not necessarily always with a zero or spaces. Sometimes a date can be initialized as today's date if appropriate. So we have created list of attributes, we have typecast them. In some cases we have provided an initial value, and then we have gone down to the operations. And in the example that I have given you, we have got get name, get serial number and change address. Now, if we really put a set and a get around each attribute in operations, we end up with data hiding, which we have discussed. But here we are moving towards encapsulation. Then you find that there are parentheses, brackets for each operation, and those brackets will contain the list of parameters. I am discussing that again a little later in this chapter. And those return values at the end, either a boolean which says this particular operation has successfully executed, or it could be the value being returned or a pointer to the value. On the left of each attribute and operation, there is the access control, and I will discuss that in a moment. But those minuses and pluses are very important for good program design. And up on top we have got the class name with a stereotype entity. As we move from high level design to lower level detailed or advanced design in the solution space, we end up with different stereotypes, not just entity. And we did have a look at some of them in the previous module. But do remember to cast your classes in relevant stereotypes. Now, if you look at the access control, which is also called visibility because it shows how visible is your attribute or your operation to the rest of the system. So you will find that there are three types of visibilities. Private, which is usually shown by a minus sign in UML, means this attribute cannot be accessed by any other class in the system. So in the example I have given name and date of birth. Name and date of birth can only be manipulated within the patient class and not by, say, the doctor class. So if a doctor class wants to know the patient's name and date of birth, guess what it will have to do? It will have to access those attributes through operations which are public. Get name, get date of birth. Sometimes it may even be age. So compute age. All these operations have got a plus. So they are public. Most attributes have got minus. So they are private. And therefore any change to these attributes is only done by that particular class. So what is a hash doing? What is a protected visibility? So when we have inheritance in our design, the inheriting classes, for example, we have got person is a patient. Then can the patient class, which is inheriting from person, change the attributes of the person class directly in the code in the patient class? If yes, then we need a protected visibility. If not, then the visibility remains private for those attributes. So it's a very important concept. I do want you to use this concept. Sometimes in some tools you will find funny signs like a lock for private and a key or open for public and so on. But each attribute and each operation can have the visibility of private and public depending on how you want to design your class. If we then look at the details of the attribute, you can see that an attribute like a serial number, name, address and date of birth, and in my example I have used name, can also have a stereotype. So stereotype is not just grouping or classification for the sake of it. It can provide control, it can provide uniformity across all attributes that are of type entity, stereotype entity. So to give that a try, providing visibility and stereotypes for attributes. Not mandatory, the stereotype that is, but very, very helpful. And then as you can see, I have provided a mapping of what we have designed in the attribute part of our class to pseudocode. And then finally, in attribute design, I have also discussed how user defined types, which are basically classes, can be used to cast attributes. So in the example I have given, address is of type address, and the type address or the class address is not provided by the programming language, but the designer, you and I, have created that address class somewhere else. So this is very important because it tells us that attributes are also classes, and let this not attributes are also classes, and we can utilize this information in order to extend our class design in the solution space. For example, we can use inheritance, we can use association to relate classes, and you will find as you go deeper into the association relationship that when a class associates with another class, it's potentially appearing as a user-defined type or a user-defined class in the definition of the other class. So I do encourage you to generate code if you have installed your tool, Star UML or Visio or whichever tool you are using, for a specific language, Java or C++ mostly. Then you will find as you relate two classes, patient and doctor, that the code that is generated for patient has got a doctor cast in it as a type or a user-defined class, and vice versa. So we are moving from just a good design to a great design, because by doing these kind of modeling, we avoid the hard work of coding and then redoing the code without the benefit of conceptual thinking. So our quality of code is better. We can eventually also apply the concepts of architecture, which we are discussing next, granularity of design, bigger and smaller size classes, and so on. And now eventually I want you in this module to have a look at how to design good operations or functions or methods. In the example I have given you, you will find I have got a operation with a visibility, usually a plus, also optionally a stereotype to help us group our operations and to apply certain constraints or limitations on them. The names of the operation: get something, calculate something, apply something, in the very basic even add and delete something. Then the name, and then in parentheses, brackets, you have a list of parameters. Now these parameters also have types. These parameters help us design a good operation. They are in fact a part of the operation. So what are these parameters? These are either a search key, for example, get name based on a user ID. So you will have the user ID and the name in brackets, in the parentheses. The user ID is something that you have filled up, ID 101, from any other part of the system. You call this particular class, which is at runtime an object, and you say get me the name, get name corresponding to ID 101. And what you get is Bhuvan Unelkar as an example. The colon is followed in an operation with the return value, which could be just whether this particular operation has been successful or not, a boolean, yes or no. Or it can contain a pointer to an array or to any other return value. Most of the time I prefer to put a boolean to say whether the operation has successfully executed or not, and whatever is the return that I am expecting this operation to return is within the brackets, within the parameter list. We can of course go much more detailed in the solution space, which is a part of subsequent courses perhaps, but for the current purpose this is good enough, wherein you have defined a class in detail in the solution space with its stereotype, name, singular common noun, list of attributes which are potential classes, which are cast to language provided types or user defined types, which have got an initial value optionally, and we have got a list of operations which are also having a visibility, minus or plus, private or public, stereotype, name of the operation, a list of parameters, and a return value. And then of course we expand each of these classes in their relationships with other classes to come up with a full system. So a program in OO is a collection of classes rather than just one class in theory, that is, and the relationship between these classes. As I mentioned, there are other types of classes, interface classes, database classes, controller classes, which you will have to provide to your classes, to your class design, in order to make it a executable runtime equivalent system. There are other diagrams like sequence and state machine, which are dynamic diagrams, which we will study. And when we study those diagrams, we will come back and update our class diagram. So you can see how rich is the class diagram at the end of these iterative and incremental cycles. I hope you are finding this course of value. I am certainly enjoying presenting it. Please remember to go to the workbook exercises and the project work at the end of each chapter and do that work, as it will help you with your team project as well. Thank you very much.